Hi there, welcome to lecture 10 of Fox, number theory. And number theory is the foundation of cryptography, which, enables secure email, communication, banking, social media. I mean, life would be completely different without number theory and cryptography. Okay, quick recap of what we did last time. Okay, so we talked about sums, how to compute sums, various tools, various ways to compare approximately big O, big theta, little theta, big omega, and so on and so forth, the asymptotic order notation. Okay, and then I introduced you to this gem of using integration to quickly and accurately approximate sums. Okay, now today we're going to be talking about number theory, and we'll start basic, but then we'll quickly ramp up and talk about the greatest common divisor, Euclid's algorithm, and so on and so forth. Ultimately, we'll use that basic number theory to prove the part 2 of the fundamental theorem of arithmetic, which is that prime factorization is unique, and then we'll end with modular arithmetic, which is the basis of cryptography and RSA public key cryptography. So some gems waiting at the end if we have time. Okay, now number theory has attracted the best, the purest of the pure mathematicians, and why? And that's because, we can formulate very simple problems that, very hard to answer. So, for example, look at this, 6. Okay, 6 is, has divisors 1, 2, and 3, divisors less than 6, and 1 plus 2 plus 3 is equal to 6. So we say 6 is perfect because it equals the sum of its proper divisors. So, how many perfect numbers can you find? Okay, we don't know. Such a simple question, we don't know. Is there an odd perfect number? We don't know. Okay, so let's at least talk about what we do know. We'll start from the basics and let's go to the board. Okay, number theory basics. Division. Okay, so, from high school, so you're dividing 27 by 6. Okay, so you're going to get 4 with a remainder of 3, and you all know how to do this. Okay. Another way of writing this is that 27 is equal to 4 times 6 plus the remainder 3. So this we call the quotient Q, and this we call the remainder R. Okay. And now, this breakdown of any number, so you can think of this as a number n, and you can think of this as a divisor d. Okay, so you have a number n, a divisor d, a quotient, and a remainder. This breakdown is fundamental, and it always exists for any number and any divisor. So theorem. Okay, and I'm going to dig into your high school vault. Okay, so we can call this the quotient remainder theorem. Okay, for any number n, which can be an integer, and any positive divisor d, which is a natural number, it's always possible to write n as a product of a quotient times d plus a remainder, where the remainder is at most d. Okay, so just as in this case, see, the remainder is at most 6. Okay, and in fact, this can be done uniquely. So there's a unique Q and R for which this is true. Q and R are unique. Okay, and I'm going to take this for granted. If you want to see the proof of it, you can look in the problems at the end of this chapter. Okay, and sometimes the remainder can be 0. So for example, 24 is equal to 4 times 6 plus the remainder 0. When the remainder is 0, we say that 6 divides 24. So 6 divides 24, and we write that as 6 divides 24. I mean, it's just a notation. Don't panic. Okay, and when if a divisor d divides n, that means that n is equal to kd for some k in the integers. Okay, remember, it's very important. The remainder is, it can be 0, or it can be 1, 2, 3, all the way up to 1 less than d. We don't typically allow the remainder to be larger than d, and that's what makes this breakdown, this quotient remainder theorem, unique. This breakdown is unique. Okay, so quick definition of there's these very special numbers, the primes. So the primes, p. Okay, so what are the primes? 1 is not a prime. The primes start at 2, and then 3, 5, 7, 11, and so on. Okay, so the prime numbers p. The prime numbers are quick. You should have seen these. Are the numbers p such that the only divisors of p are 1 and p. So there are no divisors. The only, let's say, positive divisors. Okay? There are no other divisors of P. So, 5 has only divisors 1 and 5. 2, 3, and 4 are not divisors. Okay, now basic facts about divisibility and division. Okay, so basic facts. And I think this is an exercise in the chapter, so do the exercise if you're unfamiliar with these basic facts. So fact number 1. Any divisor, any positive divisor divides 0. Okay? Because you can set the quotient equal to 0 and the remainder is then 0. So any 0 times d is 0, so any divisor divides 0. Okay? 2. If some divisor divides m and another divisor d prime divides n, then d prime divides mn. So an example, 2 divides 8, okay, and 3 divides 9, and so that implies that 2 times 3, 6 divides 8 times 9, which is 72. 8 times 9, which is, i.e. 6 divides 72, and that you can check that, and it's true. Okay. So in general, if a divisor divides a number and another divisor divides another number, the product of the divisors divides the product of the numbers. Okay, 3. Now, we can prove all these from the definition of divisibility. So I encourage you to do the exercise that proves these. Okay, if d divides m, so you have a divisor of m, and d divides n. Okay. If d divides m and d divides n, then d divides m plus n. So if you have a divisor of m and a divisor of n, then that same divisor divides the sum. So, for example, 2 divides 4 and 2 divides 6, and so that implies 2 divides the sum, 2 divides 10. Check. Okay. 4. If you have a divisor of a sum, d divides m plus n, and d divides one of those terms, d divides m, so you divide a sum and you divide one of them, then you must divide the other, d divides n. Okay, as an example, 2 divides 4 plus 6, and 2 divides 4, so this means that 2 divides 6. Notice that this wouldn't be true if 2 didn't divide 4, so 2 divides 3 plus 7 as well. But now you can't apply this because 2 divides the sum, but it doesn't divide any one of those. It doesn't divide m. Okay? And 5, if d divides m and m divides n. So d divides m divides n, so then d divides n. Then d divides n. Okay? And as an example, 2 divides 4 and 4 divides 12. So this means that 2 divides 12. Okay, 2 divides 4, 4 divides 12. Okay, and the last property that I'm going to list is that, if d divides n, so if you have a divisor of n, then any multiple of d, so x times d, where x is a multiple of d, a positive multiple of d, x times d divides x times n. And that's, all these are relatively simple facts about divisibility. Hopefully you're very familiar with them. So as an example, d 3 divides 6. And so 2 times 3 divides 2 times 6. 2 times 3 divides 2 times 6. And what is that saying? That's saying that 6 divides 12, which is certainly true. Okay, so, make sure you're comfortable with those facts. If you're not comfortable, prove them as the exercise, and you can see the proofs. Okay, and we are going to ramp it up and talk about the greatest common divisor.